In problem 4a on practice exam 3, you are asked to predict the product for the elimination reaction of this tri-substituted cyclohexane. If you look at the reaction conditions, you'll recognize that this is E2 elimination because you have a fairly concentrated base and you have a secondary alkyl halide. Go ahead and number the ring to keep track of all of the carbon atoms as you transpose cyclohexane to a chair conformation. I like to begin with carbon number 1, which is the carbon attached to the leaving group. And since we number the cyclohexane here in a counterclockwise fashion, you want to proceed in the same way on the chair conformation. So I will go ahead and number the carbon atoms, and then I will draw the substituents on relevant carbons. Carbon number 1 is pointing up on my chair conformation, therefore axial bond is up and equatorial will be down. If I look at carbon number 1 here, I see that iodo group is up and therefore hydrogen atom will be down. Carbon number 2 has ethyl group pointing up and hydrogen pointing down. Carbon number 2 on the chair is pointing down, therefore its axial bond will be pointing down. Equatorial bond will be up and in the direction of bonds 3, 4 and 1, 6. Going to carbon number 2, ethyl group is up, hydrogen is down. Carbon number 3 is pointing up, axial bond up, equatorial down in the direction of bonds 4, 5 and 1, 2. I have CH3 down, hydrogen up. I go back to carbon number 1, that's the carbon atom that has the leaving group, iodo. Iodo group is axial, and once you have the leaving group in an axial orientation, there is no need for the chair flip. If it happened to be equatorial on your first trial, you would have to flip the ring. So your number 1 consideration is for the leaving group, tosylate, iodide, bromide, chloride, and so forth, to be in an axial orientation, pointing either straight up or straight down. Next, you want to look at the alpha carbon atoms and draw relevant hydrogens. Carbon number 2 has a hydrogen atom pointing down, that is an axial hydrogen. Alpha carbon again is carbon next door to the alkyl halide carbon. And carbon number 6 has 2 hydrogens, axial and equatorial. We had drawn all relevant alpha hydrogen atoms. There are 3 of them. 2 are axial and 1 equatorial. Equatorial hydrogen will not be considered for elimination since the leaving group and the hydrogen to be eliminated need to be axial and anti-periplanar. They have to be pointing in opposite directions, up and down. Now that I see that I have 2 alpha hydrogens that are axial and anti-periplanar relative to the iodo leaving group, I need to specify the degree of substitution for each carbon atom at the alpha position. Here I have tertiary carbon and therefore tertiary alpha hydrogen, and over here I have a secondary carbon. Now that I have 2 options, 2 alpha hydrogens, I will follow the Zaitsev rule, meaning I will eliminate the most highly substituted hydrogen atom to give me the most highly substituted alkene, which will be the more stable of the 2 possible products. For the mechanism, I will draw the negative base ion, so that's methoxide ion with a negative charge. Methoxide will attack the labile hydrogen atom, the acidic hydrogen at the alpha position from the backside. The bond between carbon number 2 and the hydrogen atom will break from the sigma bond, center to center. 2 electrons will collapse toward the incipient pi bond, which will be between carbons 1 and 2. So first arrow, base, abstracts the hydrogen from the backside, second arrow, center to center, bond from bond that is being broken to the newly forming pi bond between carbons 1 and 2, and the third arrow, expulsion or dissociation of the leaving group. So 3 arrows for E2 elimination, since this is a concerted reaction mechanism. So we see that in our product, the double bond, the pi bond, will be between carbons 1 and 2. Draw the product, add the pi bond between carbons 1 and 2, and fill in the missing substituents. At carbon number 1, iodo group is gone since it was expelled. Hydrogen remains. Carbon number 2, I have ethyl group, and hydrogen is gone. That's the hydrogen we removed. Ethyl group, notice that I'm not drawing it as a wedged or hashed bond because carbon 2 and carbon atom number 1 changed their hybridization from sp3 to sp2. The molecular geometry now it's trigonal planar. Carbon number 3 had not changed. Methyl group is still pointing down. I look at my newly formed alkene and I see that the bond that I had formed is between carbons 1 and 2, since I eliminated hydrogen from the more highly substituted carbon atom in a Zaitsev fashion. Therefore, I have a Zaitsev product. I have 3 groups, non-hydrogen groups, bonded to the new alkene. I have carbon atom, carbon, and carbon. So this is a tri-substituted Zaitsev alkene. Tri-substituted Zaitsev alkene is generic designation of the product. Mechanism type is E2, and again we recognized E2 conditions by looking above the arrow. We had strong base, concentrated base, and alcoholic solvent, no addition of water in this case, a little bit of heat, and therefore E2 elimination. For E2 elimination, the reaction rate depends on the concentration of both the alkyl halide and the base. Therefore, if we were to double the concentration of the alkyl halide and double the concentration of the base, the reaction rate would quadruple.